How does a robot turn code into motion? In this module, we'll follow the full chain. ESP32 commands, motor drivers, DC motors, wheels, chassis, and power, so your robot can drive by Bluetooth or move on its own. You've already built many parts of a robot's brain and senses. ESP32 basics, circuits, code, LEDs, buzzers, sensors, distance sensing, and servo control. Now we bring those pieces together. The robot will sense, make decisions, and control DC motors to create real movement. Robot movement starts with electrical energy and ends as mechanical motion. When current flows through a motor, the shaft spins. Attach a wheel to that shaft and rotation becomes forward or backward movement. The ESP32 decides what should happen, like a brain sending commands. The motor driver delivers power safely, and the motors act like muscles doing the work. The final motion depends on speed, wheel size, grip, balance, and available power. So movement is not one part, it is a connected chain. A DC motor turns electrical energy into rotation, which makes it ideal for robot cars. Connect power, and the shaft spins. Swap the positive and negative connections, and it spins the opposite way. Increase voltage within the motor's rating, and it usually spins faster. Torque is the twisting force behind that motion. It helps the robot start moving, climb, or push against resistance. An ESP32 pin is designed to communicate, not power a motor. It can output a voltage level, like a small command saying go or stop, but only at a small current. A motor is very different. At startup or under load, it may demand hundreds of milliamps or more. That can overload a GPIO pin and permanently damage the chip. Motors can also create voltage spikes and electrical noise when switched on and off. A motor driver solves this by letting the ESP32 send safe control signals while a separate power path feeds the motor. The motor driver is the safe bridge between logic and motion. The ESP32 sends small control signals for forward, reverse, stop, or speed changes using PWM. The driver then switches battery power to the motors, which need much more current than the ESP32 can provide. It also helps protect the control board from motor noise and current spikes. One important rule remains. The ESP32, driver, and battery must share a common ground, so all signals use the same reference. To reverse a DC motor, we reverse the current through it. An H-bridge does this with 4 electronic switches. One diagonal pair sends current one way, so the motor spins forward. The opposite diagonal sends current the other way, so it spins backward. The driver exposes this through direction inputs, often called IN1 and IN2. One combination means forward, another means reverse, and other combinations stop or brake. Speed is controlled separately with PWM by pulsing power on and off. Think of the motor driver as a translator between the ESP32 and the motors. The IN pins receive direction commands. One pattern spins a motor forward, another reverses it, and stopping both can brake or coast depending on the driver. The ENA, ENB, or PWM pins control how much power is delivered, which sets speed. Motor output pins connect directly to the motor wires. Power is separate. The battery feeds the driver, while ground must be shared with the ESP32. Before applying power, always check polarity and common ground. Motors are power hungry, so treat them differently from sensors or LEDs. Give them a supply that can deliver the current they need, usually through a motor driver, never from an ESP32 GPIO pin. The ESP32 may use its own regulated supply, but its ground must connect to the driver ground. That shared reference lets control signals work correctly. If the battery is weak, motors may slow, stall, or pull the voltage down enough to reset the board. Before powering the robot, check the voltage and current ratings for the motor, driver, and ESP32. The chassis is more than a place to attach parts. It affects how predictable the robot feels when it drives. Start with symmetry. The left and right wheels should sit evenly, so both motors push against the floor in the same way. Keep heavy parts, especially the battery, low and near the center. A high or off-center mass can make turns unstable. Next, check friction. Each wheel should spin freely without rubbing the frame or dragging wires. Finally, secure the ESP32 motor driver, sensors, and cables. Loose electronics can shift, disconnect, or change sensor readings while the robot moves. Wheel design is a trade-off. Larger wheels cover more distance with each rotation, but the motor must work harder to turn them. Smaller wheels are easier to drive, but travel less per turn. Rubber tires add friction, helping the robot grip and stay on its path. Smooth plastic wheels reduce drag, but may slip. A two-wheel robot also needs a third contact point, such as a caster or skid, to stay balanced while turning. If wheels are mismatched or loose, the robot may drift instead of driving straight. Differential drive means the robot steers by changing the left and right wheel speeds separately. When both sides move forward at the same speed, the robot travels straight. If one side moves faster, the robot curves toward the slower side. The bigger the speed difference, the tighter the turn. For an even sharper move, one wheel can drive forward while the other drives backward, making the robot spin in place. That is why differential drive is so common. It gives simple robot cars precise motion using only two controlled motors. Movement functions turn repeated motor instructions into simple robot commands. Instead of writing pin directions and speed values every time, you define them once inside functions like move forward, turn left, and stop motors. Each function becomes a small promise. When it is called, the motors behave in one specific way. The main program becomes easier to read because it looks like a sequence of actions, not wiring details. Testing also becomes easier. If turning left is wrong, you fix turn left once. Later, Bluetooth buttons or autonomous decisions can call those same movement commands. Once the robot is built, resist the urge to test everything at once. Start with one motor, confirm it spins when commanded, then repeat with the other motor. If a direction is wrong, either swap the motor wires or reverse the direction in code. When both motors work, drive forward and watch for drift. Small PWM adjustments can balance motors that are not perfectly matched. If the behavior still seems random, check the simple causes first: loose wires, weak batteries, rubbing wheels, and missing common ground. Good troubleshooting is systematic, not guesswork. You now have the foundation for mobile robots. Motors create motion, drivers control them safely, and reliable power, wiring, and common ground keep the system stable. The chassis, wheels, friction, and balance shape how the robot actually drives. By wrapping movement into reusable functions, you are ready to build a Bluetooth robot car. Then add sensors for autonomous navigation.